In this video, we're just going to talk about some other features about correlation and regression. We've kind of touched on most of these ideas already, but just to kind of explain them more clearly. So we talked about lurking variables as the reason why we don't want to describe cause and effect, because most often with the data that we're looking at, it's most often coming from observational studies, and with that there can be these lurking variables. So as an example, let's see what we have over here on the right-hand side. So in this graph, we're mapping along the x-axis the number of TVs per 1,000 people in that country, and then the life expectancy of that country. So you can see in terms of extremes here, like here's Angola, very, very low number of TVs per 1,000 people, also a very low life expectancy. And then we have these values kind of in the middle, like if we look at Russia, I have 400-ish TVs per 1,000 people, and then average life expectancy in the high 60s. And then we have this clump up here of Japan, Canada, I think Australia is hiding in there, France, United Kingdom, United States. It's like the US, high number of TVs per 1,000 people, also high life expectancy. So what I want to be careful of here, so we have this moderate positive association, which means as the number of TVs increase, there tends to be this increase in life expectancy. But if I made a sentence in terms of cause and effect, can I say having more TVs per 1,000 people increases life expectancy? Like, to be dramatic about it, could I go out and buy like 100 TVs and then I'll live longer? No, it isn't actually the TVs causing this increase in life expectancy. It's these lurking variables, things that are connected with the amount of TVs owned in a country. So we could think of is, for this data, some possible lurking variables. Well, it could just be like general development of that country. Which in terms of development, what'll follow through is just healthcare and what kind of healthcare is available. And then technology is a big part of healthcare. So with countries that are a little more technologically advanced, with that will feed into better healthcare, which will lead to longer lives. But the key is, like, when you have data, you can graph any two variables together, and sometimes it will look like one is causing a change in the other. Even if you have this moderate to strong strength between these two variables, it doesn't mean the change in one is causing a change in the other. There is a trend, there is an association between those two, but we need to think about lurking variables in terms of what is strengthening that association between the two. So lurking variables is something we want to think about. Another piece is making predictions with our data. So that idea of choosing values for X and seeing what that predicts for Y. So let's go back to our airfare data. And if you wanted to fly to a destination that was 500 miles from Baltimore, how much would the ticket cost according to the model? So if we choose this X of 500, what would we expect for airfare? So if I go to my scatter plot that we're working with, I have my linear model working. The idea is if I'm here at 500, what do I expect for Y? So with that, I would just plug in 500 and that'd be $150.39. So nothing too new there. $150.39. But then what if we go to this next one? What if we're flying to Sydney, Australia? That's 9,782 miles away. So in terms of what we can do, I mean, we're just plugging in numbers to calculate. So no issue with going 9,782. And with that, it predicts an airfare of about $1,400. So let's see, $1,424.43. Which, maybe that's a good prediction, but something I want to be careful of, if I think about my scatter plot, is I'm moving into this realm that goes beyond my x-axis here. Like the highest flight we saw was around 1,500 miles away, and now we've jumped to over 9,000 miles away. This is in a very different region of our graph, and we even have moved from domestic flight into something that would be an international flight. This is where we could start to see subpopulations within our graph. If I started graphing international flights, they probably have a different trend than domestic flights. So what I need to be careful of is this estimating using values that go beyond our number line. Our first question of going 500 miles, that was fine because it's within our data set. So the line is really fitting this data and including values around 500. But when we jump to 9,000 or above 9,000, we're going way beyond the scope of our data. So we want to be careful of this might not actually be a good estimate. So do you think this model would make a good prediction? We need to be careful because it goes beyond the data. Beyond our data. So then in part C here, if you wanted to fly to a destination that was 10 miles away, so again, we can predict airfare no problem because it's just plugging in numbers into GeoGebra. So let's see, going 10 miles is $83.14. So we can make the estimate, but it's just how much do we trust that estimate? So if you're only flying 10 miles, I mean, it's hard to get a domestic flight from an airport. Maybe you have to get a private jet. And with that, the costs are going to change. So we also need to be careful here because flying 10 miles goes outside the scope of our data as well, because our data, we're seeing what minimum values are around 200. We don't actually have any values out here. Even though we can graph the line and we can make predictions with the line there, because we don't have data surrounding what's happening at these low mileage areas, we want to be careful of predictions out here. Really, in terms of predictions, we trust values that are between our smallest and largest data values, but going outside of that range, we need to be careful. So this idea is interpolation versus extrapolation. So interpolation is when we make a prediction within our data set. Extrapolation is when we go beyond, and we need to be careful of those estimates because it might be leaving out key information. So B and C here are examples of extrapolation. So just be careful in terms of where you're making predictions with your data. All right, this two more pieces, working with weak data. So what I have here is data that collected fat and sodium of burgers from fast food places. So first of all, let's just find our correlation and least squares regression line. So in GeoGebra, I went ahead and plugged in the data already. So I have my data here. Let's make our scatter plot. So two variable regression analysis. We can see from our graph, it's pretty scattered. In fact, there's this extreme value out here. And then from there, so for correlation, we have a 0.199. So very weak correlation. And then let me grab the regression line as well. So it's going to fit a line to the data. You can see it's just kind of going through, and we have this 6.0829 slope. Plus, and then our intercept was 930.0156. So we have this data, there's a weak correlation, and we have this equation of the line, and the idea is that that line would make predictions based on, given a certain fat content, estimating sodium. So let's just look at what's the average fat content and what's the average sodium content. So I plugged in fat as X and Y as sodium. So I want my average X value, so I want X bar, and I want my average sodium value, which is Y bar. And we can get that from GeoGebra. if we're in that spot that gives us correlation, you can see it gives the two means, so mean of X, mean of Y. So 34.2857. And the average Y value, which is 1,138.5714. So we have these averages. So we know the average fat content for a burger coming from a fast food joint and average sodium coming from a burger from fast food. So let's talk about making predictions here. So if a burger has 32 grams of fat, how much sodium do you expect it to have? So what we're doing is we're choosing a value for X and predicting Y. So for this case, our correlation is weak in that our data is just kind of all over the place. So when our correlation's weak, even though we can graph this line through the data, that line really isn't a great prediction source here because our data's all over the place. So yeah, we can draw it, but it isn't really fitting the data all that great because our data is all over the place. So with that, I could plug into the formula and calculate, but because my correlation is weak, this prediction line is weak too. The idea being that if I'm anywhere on this x-axis, really anything can happen for my y-axis. So it ends up happening with these cases where you have a weak correlation is that while you can find that equation for the line, it's weak for making predictions. So we don't actually want to use it. It isn't a great source. So instead, what we would do is if we need to predict what would happen for X, what we're going to use is just what on average is happening for Y, because that's kind of our best estimate for what happens just in general. So because our correlation's weak, we don't really want to follow that line. Instead, what we would do is for our prediction is just use the average. That's our best source for predicting what could happen for any, in this case, any burger coming from fast food. When our correlation strengthens, when we have moderate or strong correlation, then we definitely want to use this equation for the line. That follows our data better. But when we have a weak correlation, we don't want to use it, and instead, to make predictions, you would just use the average Y value. All right, then our last piece is to talk about Miami again, which we were talking about could be a possible outlier because we saw this very large residual coming from it. So again, with Miami, what we saw, the distance was 946 miles, and the airfare was much higher than predicted at $350. So if we go to buy a ticket and it's much more expensive, what could be some explanations of that? What's causing this spike in airfare cost? So something that might be happening is it could be the time of the year. It could be for around holiday season or spring break. It might bump up those airfare tickets because more people are flying to that region. We don't necessarily know what kind of tickets they were buying, so maybe this was them splurging for first class, although 350 is pretty low for that, but it could be the airline they used. There could be different factors that are causing this much higher airfare. So what we're going to do is compare the results to if Miami was part of the data versus what if we took it out. Because what can happen is if we see a really significant change, that suggests it's an outlier. So for what we had previously, our equation of the line, we have a slope of 0.1373 times x plus 81.7636. And we had r of 0.6953, which we interpret that as moderate and positive. So that was our data with Miami included. Now what we want to do is compare to what happens if we take out Miami. So if I go back to my data and just delete that 946, which of course it's not letting me. There we go. Sorry about that. All right, delete that. All right, re-highlight my data, 2-variable regression analysis. And what we can see is my slope changed a bit and my statistics, which are not showing up. There we go. And R has changed. So what we see now is a new equation of the line. See 0.1168 plus 83.3086. And then R changed from 0.7888. So, some things to notice, like, is there a meaningful difference between the two models? What we could do is start by comparing how did our correlation change. So the correlation changed in terms of strength. It's actually still moderate. And direction is still positive. So in terms of interpretation, correlation is actually still the same. It did get better. We can see it did change and got closer to being a stronger correlation, but in terms of interpretation, that hasn't actually changed. Something that will also show that there hasn't been change really is if you compare slope, those are very similar values, and y-intercept, also very similar values. So in terms of the equation of the line, there hasn't been a huge change there. So is there a meaningful difference between the two models? No. The model didn't change significantly, which is starting to suggest that Miami is not an outlier. Even though our residual was so large and we had this very big difference between what was predicted and what occurred, it wasn't significant enough. If it was significant enough to be an outlier, what we would see is the interpretation for correlation would change, and we'd see a significant change in our slope and intercept in the line. It would create a completely different line and different correlation. So if you want to know whether or not a value is an outlier, we do this comparison of the data with the outlier and without the outlier, and then you just see if there's been this significant change between the equation of the line and the correlation.